Hello everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm the host for today's webinar. For a number of years now, EasyPower has been the North America marketing arm for Cent Engineering, who's based in Italy and who produces the XGSLab analytical and design tools for ground grid and lightning protection for facilities. Frequently, we have as a guest speaker Yvonne Grobliar, who's based in South Africa. And normally we pre-record the presentation and Yvonne joins us live to be able to answer questions during that presentation. Unfortunately, today is due to a last-minute account visit he had to attend. He ended up on a plane at this time and is not able to join us to answer questions. So during the presentation, I invite you to enter your questions in the question submittal box in the webinar control system and be as specific as you can, because he will not be able to know what part of the presentation you're referring to without it, but he promises to respond as soon as possible via email to all the requests that are submitted. So again, thank you for joining us today. Allow me to share Yvonne's presentation.
Hello everyone, and thank you for joining this webinar on mitigating lightning related risk on photovoltaic plants using XGSLab. This forms an essential part of PV plant design in the modern era. So the webinar itself consists of lightning protection design and how that has evolved, how we have learned from previous experiences on other projects, and how we can optimize the way that we design lighting protection systems for these projects to still make them cost effective. So what we've seen in industry is that some smaller plants have very good lighting protection systems, whereas some bigger ones maybe don't have proper lighting protection systems. And this is because of the scale itself and the cost scale of the lighting protection system. It also depends on different factors which we'll discuss, like the size of the plant, the location of the plant, and the lighting activity within that area, and also the type of technology that you use within the plant, and how it's easier to protect specific technologies and also more cost effective as opposed to other technologies which could actually be more expensive to protect against lightning related risk. Just a brief introduction. My name is Ivan Groblar. I'm the Senior Technical Manager for DEN Africa. So DEN is a lighting protection company, the oldest lighting protection company in the world that's based in Germany. And I work as the Senior Technical Manager for the DEN Africa subsidiary, which is based in Johannesburg in South Africa. I've been working as a lighting protection and earthing specialist for the last 5 years. And this webinar is based on experiences and what we've learned over the last couple of years in terms of lighting protection and earthing. I do list my email address there as well, so please always feel free to reach out to me. And if you have any specific questions, I would be more than happy to answer them for you, if possible, or maybe point you in the right direction if there's someone else that I think could maybe assist you. So just an overview of the agenda and how the webinar is structured. Firstly, I would like to discuss some background around the projects. You'll see that the webinar is mostly based around a case study from a recent project that we did, and we'll discuss some background information on how the standards work and how the technologies on PV plants work, and then we'll move on over to a lighting risk assessment portion. So it's essential in the start of any project that you do a lighting risk analysis or a lighting risk assessment. according to the relevant standards to determine what lighting protection is required for the plant or the project, and also get information such as the risk that you're taking on, the residual risk, how much lightning damage you can expect, and what are your options to reduce that risk as much as possible. The risk assessment portion will mainly focus on the economic loss portion, as this is the most relevant in these type of projects. Then I'll discuss on what the standards say in terms of lightning and surge protection for PV plants. I'm using the two most popular IEC standards currently. And then I will move on to the case study itself. I'll discuss the layout, show you the layout of the plant, take you through the electrical configuration of the plant and the techniques we used to protect this PV plant. Also then on surge protective devices or SPDs, how they are tested in a very brief overview, and what we look for when we want to see if the SPDs will protect equipment against lightning or surge, what specific ratings we look for. In the case study, I will show you a quick XGSA frequency domain simulation to show you what it would look like if it was done in the frequency domain, and then move on over to the more complex XGSA time domain simulation, which is what should be used for these type of lightning simulations, as lightning is an impulse and then not a power frequency sine wave. And then finally we'll go through the results, and we'll interpret those results and see what the options would be for you to protect a PV plant, and what's the most cost-effective method to do so. So firstly, just the background of why we do this and the protection of PV plants, and how we optimize these designs by means of advanced lightning simulation. So as I mentioned in the beginning, with the increase in size of PV plants in modern days, we used to see plants of 5 megawatt peak and 10 megawatt peak. They were considered as big PV plants a few years ago, not too long ago actually. And nowadays we've moved over to PV plants that exceed 500 megawatt peak, up to 800 megawatt peak. And with this increase in megawatt peak size, it could be that the lightning risk also increases, and that the equipment itself becomes more expensive. So it's a bigger plant or bigger portion that you need to cover to generate that megawatt peak output. And with this, when renewable companies go to tender for a project against other companies, they tender with a cost per kilowatt peak value. So it could be US dollar per kilowatt peak, or in South Africa it's rand per kilowatt peak. And that's how they get awarded the tender. One of the biggest drivers is the cost per kilowatt peak. If you add lightning protection or surge protection, that affects that cost per kilowatt peak. And someone that maybe installs very excessive lightning protection will have a higher cost per kilowatt peak, as opposed to someone that installs nothing. And the person that installs no lightning protection would actually win the project, but the plant's not properly protected. So this webinar aims to guide you to go find the most cost-effective and most feasible protection solution, to still have a competitive cost per kilowatt peak value, and still be able to win projects, but to still ensure that the plant is adequately protected. Now, the size of plant itself is not the only driver of the risk. It could be that you have a small plant in a very high lightning dense area. So you also have to look at the location and the lightning activity in the area, not just the size of plant. Further to that, different technologies also require different types of protection. So for an example, if you decide on a PV plant between something like a string inverter system as opposed to a string combiner box system, those two carry different protection requirements and therefore also different costs. So that could also be a big driver in what your cost per kilowatt peak value would be at the end if you add the lightning protection. In the IEC 61643-32 standard, that's the most commonly used IEC standard for PV at the moment. So in this standard, it's actually a standard for surge protective devices installed on the DC side of PV plants. But they also give a lot of guidance into what external lighting protection should look like. That's your air termination, your earthing, and things like that. What type of SPD should be installed also on the AC side. And in that standard, it is recommended to install at least a lighting protection level 3. So just to understand how lighting protection levels work, you can see in this table at the bottom, it starts from the lowest level of protection, which is lighting level 4, and moves its way up to the best lighting protection level, which is lighting protection level 1. In a lighting protection level 4 requirement, it means that it will protect for lighting strikes between 16 kiloamps up to 100 kiloamps. And as you move up to lighting protection level 1, the higher band also increases, so we protect up to 200 kiloamps, and also goes closer to 0. So you can see it also starts protecting from 3 kiloamps. That means the band widens, so you cover a bigger range of lightning strikes with a level 1 as opposed to level 4. So the standard actually recommends a lighting protection level 3, meaning that it will start from 10 kiloamps upwards to 100 kiloamps. The reason is just because of the lower band in this region. We see that the majority of lightning strikes in these rural areas where PV plants are being built is actually lower than 16 kiloamps, meaning that if you installed the lowest level of protection, you would miss some of the lower peak valued strikes. For that reason, the standard recommends at least a lighting protection level 3, but this is only a recommendation. And different mitigation techniques can therefore be applied to reduce the lighting risk. It won't be fully compliant if you don't have a full lighting protection system. You cannot claim that you have a lighting protection system. You need all the components. But you can use a targeted approach where you would add maybe more earthing or reduce earthing and add more surge protection. And you can go for specific areas of residual risk and have a more targeted approach to optimize the design itself. Now moving on to the lighting risk assessment portion. As I mentioned, it's according to the IEC standard in this case. So the IEC standard that we talk about for risk assessment is IEC 62305-2. This standard is actually written for buildings, as there's no lighting risk analysis standard written for PV plants as of yet. The lighting protection standards for PV, however, do recommend that you use this method and adopt it in a way that you could use it on a PV plant. So this just forms part of experience and best practices to be able to apply this to a PV plant, but there's no formal standard for PV plants, and it could be very subjective. So this is an example of some of the outputs when we do a risk analysis for PV plants. You can see that on the right we have a lighting ground flash density map. So this is of South Africa, but it is available in all countries for country-specific measurements. But there's also the optical transient dispersion map from NASA, which is a global overview that's also quite accurate, and you can use that as well. It's openly available. And what lighting flash density means is that we measure lighting activity based on the number of lightning strikes per square kilometer per year. So if the lighting flash density is 1 strike per square kilometer per year, it means that for a square kilometer area of a plant, it will get struck at least once a year. If the flash density was 0.5, it means that plant will get struck once every 2 years, as an example, but this is just a probability calculation. Now, if you use the lighting risk analysis method and you apply lighting risk analysis, it highlights different levels of risk. And as I mentioned, that means you can explore various options for lighting and surge protection to go for a targeted approach and go for the most relevant or prevalent risk first. A lot of things such as cable shielding, routing and bonding all contribute to reduce this residual risk. It's not necessarily just lightning protection itself as an air termination or surge protection or earthing system. You can do things like cable routing, precaution and bonding and things like that to reduce the risk as well. As I mentioned before as well, the standard does not allow for something like half of an LPS or half of a lightning protection system. You need all the elements of a lightning protection system, and they all must be compliant to make sure that you have a compliant lightning protection system. If you, for example, don't have proper earthing and it's not according to the mesh size or the earthing requirement size, that actually will not form part of a fully compliant lightning protection system. So you cannot do the calculation in the standard with half of a lightning protection system. But bearing in mind, there are ways to go for a targeted approach. What you can see in this graph at the bottom here is an example of an output that we did for a specific PV project. In this case, you could see this is now in South African rands, the currency, but it could be done for any currency. You can see that if the designer, the PV plant designer, did not install any lightning protection, surge protection, earthing, no mitigation at all, the expected losses would have been around 9.5 million rand per annum due to lightning. If they added some techniques but not the full external lightning protection system, so they added surge protection, bonding, they took care of cable routing precaution, and some earthing was installed, the risk is immediately reduced to about 3.3 million rand per annum worth of lightning related losses, lightning related damage. And then lastly, if you install a fully compliant lightning protection system with all the surge protection, all the earthing as per the requirements, and you install air termination rods, the risk was reduced to around 50,000 Rand per annum. So it had a very big impact on the residual risk that they were expecting towards the end of the, or per annum. Now, talking about a fully compliant lightning protection system, this is just an overview on what such a lightning protection system consists of for a PV project. So you can see firstly the external portion of it. We have an air termination rod mounted at the back of the PV modules. There are different ways to do this. It could be very custom. So we do this typically to match the wind load requirements and the wind load ratings of the PV system itself. We take care that separation distance is maintained and kept at the corner so it doesn't flash into the PV module if it gets struck. And then we move down to a down conductor system where we make use of specific connection elements across the bearing if it's a tracking plant. And we use the pile itself into the soil as part of the down conductor system, and then that connects to an earthing system underground, which could be of different types of material. The standard talks of the earthing requirements for a PV plant to be 20 meter by 20 meter meshes or grid under the plant. But they do say for larger plants you can increase this to 40 meters by 40 meters. The reason for that is that the surge protection that's installed in PV plants are not rated to very high peak values. That's not a manufacturer thing, it's according to the standards and the way they get tested. But if you do get a lightning strike somewhere within the PV facility, you need immediate current dispersion through the mesh to make sure that not a lot of energy makes its way to a specific area like a combiner box or a transformer, because if all the energy moves to one point, that surge arrestor would be overstressed and you would go and exceed the peak values or the energy values that it can handle. So if you have sufficient meshes, you have sufficient current split by the time it reaches the equipment and the SPDs, and therefore the SPDs will not be overstressed. And that's one of the things that we talk about in the case study as well. And then lastly, the surge protection. So in previous webinars, we spoke about the difference between a type 1 and a type 2 surge arrestor, but we'll go over that briefly in this webinar as well. The surge protection is just installed at all electronic equipment to make sure that the electronic equipment is not damaged due to direct lightning strikes or any induced effect or surge or secondary effect from lightning as well. If you understand the functionality of each of these components, you can use that in your targeted approach to reduce the risk. And you can do this also by doing advanced simulation using XGSLab to predict where the most losses will be within the PV area. The standard requirements for lightning and surge protection, the standards we mentioned, is this IEC 62305 standard, which is the main standard for lightning protection in IEC countries, and also the IEC 61643 standard, specifically -32 for PV in this presentation. So as per these two standards, if an external lighting protection system is installed on the PV plant, you need to have at least type 1 plus 2 SPDs installed, which means they should cater for lightning and surge current. The earthing system must consist of at least these 40 by 40 meter meshes, and bonding in the PV area must be done with at least 16 millimeter squared copper cable. If you don't install external lighting protection, there's no formal requirement for earthing, and type 2 SPDs are sufficient, so they are actually made to protect against the secondary effects from lightning, surge or induced surge or switching surge could be as well. And the bonding may be reduced to at least 6 millimeter square copper as opposed to the 16 when you have direct lightning currents entering the plant. Now, if we move into the specific case study to show you how all of this is applied, we addressed specific risks and we made decisions based on where we expected the biggest annual residual loss, and we targeted that specifically to reduce the cost but still maintain an adequate level of protection and still take on a small risk, a residual risk. This project is a 90 megawatt peak PV project, which is located in an area of a lightning flash density of 2 strikes per square kilometer per year, which is not excessively high. It's quite average, and you can see an overview of the plant on the right hand side. So the plant consists of multiple blocks allocated with colors, and they all feed into a central transformer system that all combine to the main substation. The plant consists of a tracking structure, meaning that the rows actually track the sun, and the plant moves and follows the sun to get optimum output. The tracker rows, if I zoom into a corner of the plant, you can see a tracker row is roughly 60 meters long, one of these rows, and they are connected. Every second row is connected in the middle with a driving arm that drives 2 rows at the same time to track the sun. So if we had to split it in half, it's roughly 32 meters to split the tracker in half, and you would have a smaller sort of mesh size. So this would aid in the dispersion and distribution of lightning current. The earthing in this plant consisted of galvanized steel earthing. The reason for that is that it's very cost effective, and the soil resistivity is a good indicator of the corrosiveness of the soil within the plant. And this had a medium level of resistivity, meaning that it's not very corrosive, so the galvanized steel earthing could be used. If the resistivity was very low, it would mean that it's probably corrosive, and you should use something like copper for the earthing instead of galvanized steel to still maintain the 20-year lifespan of the PV plant itself. Now, the biggest aim of the study was to reduce the earthing and also not installing a lighting protection system within the PV area of the plant. So a lighting protection system will still be installed at the transformer stations, the central locations, but in the PV area where the modules are located, no lighting protection system will be installed, and we still wanted to further reduce the earthing requirement. So the first option would be to go for the 40 by 40 meter mesh intervals from the standard, which means we split the trackers in half by making use of underground connections and the above ground driving arms as natural elements, and the outsides of the long 65 meter row will be connected to the galvanized earthing. And this actually forms small meshes of, say, 32 meters by 6 meters, which is the spacing in this case between the trackers. So you have all these small 32 by 6 meter meshes. So if a strike had to occur anywhere within the plant, it will dissipate quite quickly. The option was to remove the center connections and just leave the driving arms, making some of the meshes 65 by 6 meters in size, which will exceed the minimum 40 meter requirement if you go from a north-south direction. So this saves a significant cost, but we wanted to calculate what the residual risk would be if we use this type of approach. The project further from an electrical perspective uses string inverters, as I mentioned. So all the PV modules feed into the string inverter. The string inverter can take up to 24 DC strings. And from the string inverter, it feeds with 3-phase alternating current to a central transformer location. And all these multiple central transformer locations will feed to the high voltage yard where it's connected to the grid. Now, the type 2 or the string inverters have type 2 surge arresters integrated inside of the inverter on both the DC and the AC sides. That's standard when you purchase them. Some manufacturers do offer to upgrade this to type 1, but most of them actually don't. According to the IEC 61643-32 standard, type 2 SPDs are sufficient to be used on the DC side of string inverters. The reason is that we have 24 strings on the DC side of the string inverter, meaning that there's a lot of attenuation before it enters the inverter. So if you have induced surge or lightning strikes in this area, that energy will split between the 24 strings, and attenuated effect will enter the string inverter, and the type 2s will be able to handle that and not be overstressed. However, on the AC side, you only have 3 strings, which means that you have less dissipation and less attenuation. And for that reason, you still need type 1 SPDs to be installed on the AC side of the string inverter and the low voltage side of the transformer. So this is something that we also want to look at, is if we will see the type 2 SPDs inside the string inverter being overstressed if we change things like the earthing mesh sizes on the PV plant itself. Now, to be able to determine if SPDs will be overstressed, we firstly need to understand the difference between 10 by 350 microsecond, 8 by 20, so lightning and surge, and also what we want to look for to see if the SPD is overstressed. What could overstress it? On the right hand side, you can see an image of a lightning impulse that's taken from the IEC 62305 standard in part 1. This denotes what the 10 by 350, or explains what the 10 by 350 or the 8 by 20 means. So for a direct lightning strike, we talk about 10 by 350 microseconds, which means the impulse of the lightning strike will reach its peak value in 10 microseconds, which is period T1, and it will decay to 50% of the peak value in 350 microseconds, which is T2. For nearby strikes or the induced effect from lightning or switching surges, we talk about the 8 by 20 wave shape, which means it will reach its peak value in 8 microseconds, which is slightly faster, but it will decay to 50% of its value in 20 microseconds. So the decay process is much faster. Type 1 and type 1 plus 2 SPDs will protect against the direct lightning strikes from the 10 by 350 microsecond wave shapes, but type 2 SPDs can only protect against 8 by 20 microsecond wave shapes. The reason for that is something that is known as specific energy. So specific energy is the area under the curve of the amp squared. So what we do is we integrate the peak current in squared, so it's integration of amp squared, and we get the specific energy. The area under the curve is obviously much bigger for a direct lightning strike as opposed to a nearby strike, and because of that, the specific energy is much more. That means that the type 1 surge resistors can handle much more specific energy and energy as opposed to a type 2 SPD, and it's not just peak value that we need to look at. We do this calculation also with something known as the Joule integral that you can use as well if you want to do the calculations manually, but the specific energy is measured in joule per ohm or amp squared seconds. They could be used interchangeably, and I will be using them interchangeably throughout the presentation as well. If we look at an example of what we have installed inside the string inverters and what we want to see, what we want to analyze and investigate to see if it's going to be overstressed. Firstly, for a typical 10 kA rated type 2 SPD, the specific energy limit, You can see here, and in the graph on the right, we have the 10 kA 8x20 impulse, and the specific energy is the integral of the amp squared under this curve. And the specific energy rating for a 10 kA type 2 SPD with a typical technology, a commonly used technology, is 1415 joule per ohm, or 1415 amp squared seconds. Whereas if we look at something like a 35 kA rated 10x350 microsecond type 1 SPD, the specific energy rating is 306 kilojoule per ohm. If we break it down to what is installed within this plant, the type 2 SPDs on the AC and the DC side of inverter can only handle surge with a peak value of 10 kA. That means the specific energy limit is 1415 amp squared seconds. But at the transformer station, we use the type 1 SPD that can handle 306 kiloamp squared seconds. And at the O&M buildings and things like that, for example, the standard requirement is 50 kA for lighting level 3, and they can handle up to 625,000 amp squared seconds. So this is what we will look at to see if this will be overstressed during our investigation, as well as the peak values, to make sure SPDs will remain intact after a lightning strike. So lighting consists of high frequency behavior. If you had to compare a lightning strike impulse to the rise time of a sine wave, lightning strike is in the region of 25 kilohertz sine wave in terms of its peak time. If we change that, if we look at something like a first negative stroke, we talk about 250 kilohertz. For first subsequent stroke, it could be up to a megahertz. So it's got extremely high frequency behavior. And because of that high frequency behavior, the ground potential rise is very localized. So it creates a very steep, localized ground potential rise. For that reason, we can isolate a block for the study and only focus on a specific block and still maintain that ground potential rise within that single block. This is beneficial because if we move over to the time domain simulation, that can become quite rigorous and time consuming. And if the plant is very big, a simulation like that could run for weeks on end. If you reduce the block size, it's still possible to use that for the results, and also it reduces quite heavily on simulation time and processing time for the computer as well. So in this case, we used a single block with a transformer station and multiple string inverters. In the time domain simulation, in this case, we injected what is known as a first negative lightning stroke, meaning that the lightning stroke carries negative polarity. The selection was 50 kiloamps, according to the IEC 62305 standard for first negative. And this covers a 90% probability. So 90% of all lightning strikes recorded over the world is of first negative type. So we cover a 90% probability. We do both direct lightning strikes on the PV plant, and we also investigate nearby strikes if the strike had to be directly outside of the plant or up to 500 meters away, which I'll explain a bit later as well. The simulation consists of 167 different frequencies. So how it works with XGSA in the time domain is that the impulse consists of multiple frequencies. In this case, it was 167 different frequencies. And the simulation goes and calculates the results, current, voltage, magnetic field, ground potential rise for each point all over the plant 167 times on each point. And that's why it becomes time consuming, and it's beneficial to reduce the size of the plant that you are simulating to a single block. The setup, as you can see, string inverters are located here next to rows in the central areas where the roads are located. And the transformer station, the central transformer station, ties everything up somewhere here towards the right-hand side of this image. So we will be measuring specific energy and current at all the inverters that are close to the lightning strike, also at the transformer station itself. And for interest, we also measure voltage on the PV DC strings behind the PV modules to see what the induced voltage is from the lightning strike itself, to see if the overvoltage will cause damage to the PV modules. So as I mentioned in the first simulation, we terminate lighting at the transformer station where there's an earth grid. There is actually a lighting protection system installed just at the central transformer stations. And then we terminate another lighting strike 6 meters outside of the plant, so just outside of the boundary of the PV perimeter, and then 500 meters away. And this ties up with what the risk assessment standard says you should be looking at. And then we do this iteratively. So we first do it for the option that we want to explore of having the 32-meter mesh option, having the central connections at the tracker arms, and then later reducing that to or increasing the mesh size and reducing the material by going up to 65-meter options to see what is the risk by not adhering to the 40 by 40 and slightly allowing for bigger meshes and less current distribution and dispersion throughout the plant. In this case, you can just see, so the 6-meter strike is directly outside of the plant, and then the 500-meter strike would be towards the left here, 500 meters outside of the plant. Now, after doing the simulation, we can then go through the results and interpret what we measured in terms of the results. Firstly, if we look at the 32-meter option, we measure at the inverter 1, 2, and the transformer. Just before I show you the results, you'll see that some of the impulses are of negative value. This is purely just because XGS actually allocates convention of current flow, and if it's leaving or entering a node, and it just allocates a positive or negative sign. They could all be used as positive. It's just to show convention of current flow. To be able to get the specific energy, I mentioned that you calculate the area under the curve of the amp squared. Which was also, this was great support from XGS, by the way. So in the past, we had to export the CSV file of all the data points to something like MATLAB and do the integration in a different software. We also did this in Excel by using the trapezoidal method, but these are a lot of data points and it becomes very difficult. The calculation methods become very slow. So after discussing with the developers of XGS, they've now included the amp squared second for you in the graph already. So the software calculates this amp squared second value for you. So if we look at the results, you can see firstly for inverter 1, we're looking at around 9 kiloamps of peak current with a specific energy of around 12 kiloamp squared seconds. And just maybe the inverter 1 is the inverter that's closest to the transformer, and inverter 2 is further downstream to see the effect further away. Secondly, the effect on inverter 2, you can see it's around 3 kiloamps of peak value. The amp squared second value is reduced to 873 amp squared seconds. And lastly, at the transformer, you can see there's a very high peak value, and we talk about 43 kiloamp square seconds of energy. If we do this simulation again, for the 65-meter option where we increase the mesh sizes with less material, we now have less dissipation theoretically and less current distribution. So the energy should be higher. Firstly, you can see for inverter 1, again a 9K at peak value. This is quite close to the transformer. The specific energy is around 13 kiloamp squared seconds. For inverter 2, it's around 4 kiloamp of peak value and around 1.6 kiloamp squared seconds. And at the transformer station, again, the values are quite high with specific energy up to 43 kiloamp squared seconds. If we summarize these results, you can see that in the first case, we have the 65-meter options. The specific energies are listed there. And on the second option of having every 32 to 35 meters of earthing meshes, you can see the specific energy values listed there. On the right-hand side, based on the specific energy reduction, you can see by moving to a smaller mesh size and more current distributions, you can see the improvement. At the transformer station, we don't see that difference because this is before any splits have taken place. The lighting is terminated at the transformer station. But further downstream, if I have earthing every 32 meters rather than 65 meters, I have a 10% improvement. And if I go further away downstream to the second string inverter that's further down the road, it's almost up to 50% of extra current dissipation that you'll see, and a bigger chance for the inverter surge protection to survive. We mentioned that the SPDs inside the inverter, especially on the AC side, can handle 1415 amp squared seconds. In the 32 to 35 meter option, you'll see that inverters further downstream away from the transformer station will still be protected and the surge arresters will not be overstressed. However, the inverter very close to the transformer station is still at risk, and the transformer station is protected with a type 1 SPD, so that's no concern there. If we look at the option of going 65 meters away of earthing meshes, and we increase the mesh size, double the mesh size basically, you can see that even further away, string inverter 2 was still overstressed in terms of the limit on what we can expect. So there's a little bit of a trade-off there. You can either go for type 1 SPDs, they can take more specific energy, or you would have to increase the amount of earthing that you have to make sure that the type 2s inside the inverter will not be overstressed. Then we look at a nearby strike just outside of the plant 6 meters away, and then we measure at inverter 1 here on the left and inverter 2 on the right, and then we also measure the DC string voltage from the induced voltage on the strings. Firstly, at inverter 1, you can see immediately the energies are much lower. We talk about 154 amp squared seconds. This is for 65 meter earthing option. At inverter 2, it's 475 amp squared seconds further away. The value is a little higher. I believe it's because there's more earthing concentrated that way, which maybe forces lightning current to go into that direction. And then lastly, the PV string voltages are also very high, around 90 and 60 kilovolts between the two DC strings. We do this again by adding more earthing, so we go for the 32 meter option. Again, for inverter 1, we see 251 amp squared seconds of specific energy, and for inverter 2, we also see 217 amp squared seconds of specific energy. If we look at the results, all the specific energy is below the limits of the SPDs, as they were designed to protect against induced effect or surges, so there's no concern there, even if you have different earthing options, and that's why the standard also will not dictate specific earthing requirements necessarily to account for current splits. The voltage difference between DC strings is around 31 kilovolts. So what this means is that the PV modules actually have a limit of between 8 to 12 kilovolts of impulse voltage that they can withstand. So this exceeds that. During nearby strikes, there's a very big risk of losing the electrical components in the junction box behind the PV modules. Now, there's not a lot you can do to protect against this that's feasible. The best you can do that makes sense is to have all the PV DC strings shielded or running in metal conduits, or make sure the loop sizes are smaller, so you don't have a very big loop size between positive and negative DC strings. If you make the loop size smaller, the induced voltage on them is also lower. Another option could be installing surge protection at each PV module, but this would not make sense from a financial perspective. Then lastly, we do the calculation again for a strike 500 meters outside of the plant. You can see at inverter 1, the energy is extremely low, and at inverter 2, the energy is also very low. If you look at a summary of the results, you can see the specific energy is very low, so there's no concern for lightning strikes 500 meters away, as this will not overstress the SPDs. It's far below the specific energy and the peak current value limits of the SPD. So to conclude, lightning protection systems are used to control the interception of a lightning strike and also the conduction and the dispersion of the lightning current through the soil and through the earthing system. If we have the 40 by 40 meter mesh earthing system as per the requirement from the standard, the dispersion is quite adequate and sufficient to ensure that the SPDs will also not be overstressed during that direct lightning current strike. By adjusting the mesh size, we can save a lot of material costs by adding a slight increase in residual damage annually on what we expect in terms of losses. If we go for a targeted approach and we look at specific parts of the inverters and electrical equipment that we want to protect with specific type of SPDs, but by reducing the earthing system as an example. Type 1 plus 2 SPDs are always required to reduce the risk to the maximum level, and they ensure the lowest residual risk, but with sufficient current split in the PV plant, that can be reduced to type 2 SPDs, which are more cost effective to use, but you would need to have sufficient earthing splits. I would also recommend that you use a lighting risk assessment to verify this and make sure that you don't do this in an area where the lighting risk is extremely high and the lighting flash density is very high. So always use a lighting risk assessment to make these type of decisions on what approach you want to use. Is your risk more surge related or more lightning or direct lightning strike related? And the aim then of this was then that there's a trade-off in these big plants. So you can either install type 1 SPDs and ensure that the inverters are mostly protected and the residual loss is very low, or you could increase the earthing and have more earthing meshes, but this carries a cost of installation and material cost, and it depends on what makes the most financial sense when constructing this plant. I would like to say thank you for attending this webinar. I hope that the information you see was beneficial, and that this maybe changes the way that you see the approach of lighting protection on PV plants. And as I mentioned in the beginning of the webinar, please feel free to reach out to me if you have any questions. I would be more than happy to answer all of them. And thank you once again, and thank you to the team at EasyPower for allowing us to present on the webinar again. Thank you.
I always enjoy Yvonne's presentations. It's like going back to school. Just as a quick follow-up, the software that he used to do the analysis and generate the results is the XGSLab tools that I was referring to. As you leave the webinar control, you can ask for additional information either on the hardware from Dane Industries or from a software that would come from EasyPower. So thanks again for attending, and we look forward to having you join us in the future. Have a good day.